Okay, so we were looking at the TDGL equation in its dimensionless form, because that was the sort of easier one to look at. So, that is the dimensionless form, and we found that there are 3 fixed points, homogeneous solutions, which are just 0 and plus minus 1, and then there is this kink solution, which obviously is of slightly higher energy than the homogeneous solutions, which connects the plus 1 to the minus 1. Okay. So, that goes under various names. Nivedita, you would be familiar with instanton and all that. They were asking why it is called instanton earlier. So, I gave some what I thought was an explanation. Anyway, so this kink is very famous in all branches of physics. Okay. So, the next thing I want to do is actually compute the surface tension cost of this kink. Okay. So, basically maybe I will just keep the kink up here and the anti kink, and then take it from there. Okay. So, my next calculation is the surface tension due to the kink solution. Kink solution. And for that I have to go back to the expression of the free energy. So, the free energy for the kink solution is simply G psi s. So, now this is space dependent. It is equal to, I am going to break the integral up into dz, which ranges from minus infinity to plus infinity, and then it is sort of translationally invariant in the other directions. It is a sort of just a one dimensional solution. So, that is the area of the transverse direction. So, it is just that, and then in the curly brackets you have minus psi s squared by 2 plus psi s4 by 4 plus half, now we just take the one dimensional derivative ds by dz the whole squared. Okay. So, I want to calculate the difference in this energy and the energy of the homogeneous state, which is simply G psi 0, which is either plus or minus 1, and that is simply A dz, again just using the same notation, minus psi 0 squared by 2 plus psi 0 squared 4 by 4. And this term is missing, of course, because there is no gradient in the homogeneous solution, and even this you can simplify. I have just written it that way for a particular reason, which will become obvious in 2 minutes, right. So, basically the surplus of free energy is G psi s minus G psi 0, and that is equal to A. Now, let us pair of these terms, minus infinity to plus infinity dz. This one becomes minus 1 over 2 psi s squared minus psi 0 squared. This one becomes 1 over 4 psi s 4 minus psi 0 4, and the last term is simply half d psi s over dz the whole squared. So, I am just telling you a sort of simple way to calculate this. I mean, you could just do it directly from the integral expression basically. Okay. And if you recall the first integral, my first integral, I do not know whether I still have written down here. Oh, I actually have it out there. Huh? So, my first integral was that. So, I can basically just write this first integral. Let me just sort of use the notation I had earlier. I write the first integral down as 1 over 4, which is psi 0 squared by 2 minus psi 0 4 by 4. Okay. So, basically I have just identified that term in there as the first integral, and this gives me the result that this quantity is basically simply half, this quantity is simply half d psi s by dz the whole squared basically. Okay. Is that okay from the first integral? If I just sort of take these guys on that side, I have just that, and that's the term inside the bracket basically. Okay. You can just cross check it if you have any doubts. So, this expression combines with that expression and it gives a minus infinity to plus infinity. D psi s over dz is just the derivative of tanh z. So, that is the derivative of tanh z is sec 4. So, that is sec 4 z divided by root 2, and then you will get factors of, I think, some overall 2 root 2 basically or some such thing, sec 4, yeah, you will get an overall factor of 2 downstairs, I think basically, yeah. If you do the derivatives and take the squares, etc., you should just sort of, I mean, wherever I skip a line of algebra, just do it yourself. Okay. So, basically, the surplus of energy is 2 root 2 by 3. This is a standard integral in Gradstein and Rezek, and that is 2 root 2 by 3 a. So, the surface tension is identified. Obviously, the surface tension is the factor that multiplies the area. So, that is the surface tension of the interface basically, and that is what is going to drive phase separation. So, again, now be clear in your mind, the highest energy is of the 0 solution, the lowest energy is of the plus minus 1 solution, and the kink is in surplus of the plus minus 1 solution by this factor, and this factor of course it vanishes in the thermodynamic limit, because those factors are proportional to the volume and this factor is just proportional to the area, as you expect the surface tension to do, right. So, basically you have a volume has one higher dimensionality than the area. Okay. So, that is the surface tension, and maybe I will sort of just keep this in mind, because I will need to use this later. So, that is 2 root 2 by 3, and let us put that in a box. Okay. I hope the hierarchy of solutions is clear, where they sit on the free energy scale. As always, you will proceed to the solution with the lowest free energy, that is a given. Now, let us sort of go to the case of a curved interface, because so far I have just been dealing with the flat interfaces. Huh? So, let us go to the case of a curved interface. So, I call this the heading is equation of motion for interfaces and growth laws. Okay. Remember, I wanted to characterize this evolving morphology in two manners. One, I wanted to find out what is the length scale as a function of time, and the second, I wanted to find out what is the correlation function of the morphology, which characterizes the sort of pattern, the emergent pattern from the system basically. Okay. That is what I am going to use these King solutions to do, as a matter of fact. Okay. So, let us now look at a curved interface. Let me draw a scheme, sort of, let us look at a typical curved interface between a phase -1 and a phase +1. Okay. Obviously, curved interface is not going to be just a simple kink solution, it is going to be a little more complicated than that. Okay. And I take, sorry, this is not plus, this is +1. Okay. And I take the normal coordinate as I, n. That's the direction along which the sort of order parameter changes from -1 to +1, and I take the tangential coordinate as a vector. So, a vector just is the area and it is d minus 1 dimensional. So, this is d minus 1 dimensional, where d is the dimensionality. Let us try to write the TDGL equation down in terms of these curvilinear coordinates, and the sort of first thing you have to identify is the following. So, if you want to take a grad of psi, which is you need the grad squared psi in the TDGL equation, that is simply the psi does not change along the tangential direction, it only changes along the normal direction. So, it is basically del psi over del n at constant t n hat. So, that is a unit vector along the n direction, and you have the change along the n direction, and there is no change along the normal direction, along the tangential direction basically, right. That is why I have set up these curvilinear coordinates. I need the second derivative also. Help me out with the second derivative. The second derivative is going to be 1 second derivative of this del 2 psi over del n squared with t fixed, the tangential direction fixed, n vector, and earlier there was an n vector, so that is going to mean n vector dot n vector. Okay. That is one term, and then you will also have to now take the gradient of the curving normal coordinate, because the normal coordinate also changes in space as you go along. So, the second term is simply going to be plus del psi over del n at constant t, divergence of the n vector. If you had a flat interface, then the second term would be identically 0 basically, because the normal vector would be the same everywhere basically, right. So, that is the second sort of factor that we need. Okay. And finally, I am going to use the following identity, which is the cyclic identity, which you are all familiar with, that is del psi by del t along the tangential direction at n fixed times del t over del n at psi fixed del n over del psi at t fixed is just equal to -1. I hope all of you are familiar with this cyclic identity, right? This is always true when you have a sort of set of partial derivatives basically. Okay. So, now we sort of put all this together. I am going to put this, so I want on the left hand side of the TDGL equation del psi by del t. So, del psi by del t I just get from here. What is del psi by del t? It is just equal to minus del psi by del n at constant t del n by del t at constant psi. Okay, that is from the cyclic identity, and then the right hand side is simply psi minus psi cubed as such plus grad squared psi. This is just 1. So, grad squared psi is plus del 2 psi over del n squared at constant t plus del psi over del n at constant t divergence of n. Very sort of straightforward sort of playing around with curvilinear coordinates. Okay. And at late times, if the interface is almost flat, you can assume that this the functional form there is almost the static solution. So, you can sort of set this to 0, assuming a local kink is established. Okay. Strictly speaking, this only holds for a flat interface, but for a gently curving interface at late times, it is almost true. Okay. So, you can sort of drop this term, which was why I switched to these curvilinear coordinates. Okay. Cancel del psi by del n from both sides, and you find the final equation I am after, that del n by del t at constant psi is equal to minus divergence of n. What does this equation physically mean? That is a sort of important thing I want to emphasize. At constant psi, so if the interface is moving in that direction, that derivative is taken at constant psi. So, that is just the velocity of the interface basically in the normal direction. Okay. And that is the that is how the n hat changes. This is what is called the curvature, as a matter of fact, of the interface. Okay. So, that is this important equation, though simple enough, that the velocity at a point A along the interface, and the velocity is in the normal direction, is equal to minus grad dot n, and that is simply minus the curvature at the interface. Let us put this in a box. This is known in the literature as the Kahn-Allen equation. Kahn was a very versatile theoretical physicist who did most of his research in the field of material science. And Kahn was actually, I do not know whether you are aware, have you heard of these quasi crystals? Huh? So, Kahn was actually the first one to give the explanation of why this guy, this Israeli Shechtman, saw quasi crystals in his experiments. So, he is a very bright guy. His name is also on the phase separation model as the Kahn-Elliott equation. Okay. So, very sort of well known guy in this field. Okay. Let us quickly do, okay. So, that is the analysis. Yeah, please.
That second last equation.
Yeah, just 1 minute. Let me have a drink of water. And let us take a 2-minute break. Yeah, what?
The equation where you crossed out that term.
This one?
No, the third one.
This one okay?
Yeah, that. Can you explain that?
Yeah. So, what I did was I started with the TDGL equation and wrote it in curvilinear coordinates. Okay. So, my TDGL equation was just that. I am writing the left hand side and the right hand side in curvilinear coordinates. Del psi by del t I get by taking this term to that side. So, that is the left hand side. This is the statement that there is local equilibrium. So, locally you have a kink profile, and that is that term out there basically. So, this because you locally have a kink profile, that term drops out by definition of the kink. Okay. So, that is just 0, and then I should have said this, I then cancelled del psi by del n at constant t from both sides. Okay. Okay, so first thing I am going to do with this equation is whatever a physicist always does first when presented with a research problem. Let us do dimensional analysis. Okay. So, I know the length scale is L as a function of time. That is sort of clear from my experiments and my pictures. Yes.
The second last term looks like coming from this total derivative of n cap goes to 0.
This equation? That one? Yeah, that is just once you have cancelled out the local kink solution, then it is just from this equation del n by del t, how the unit vector changes if you keep psi as fixed. So, it is the direction in which the interface is moving basically, because if psi is to be fixed, psi equal to 0 defines the interface. So, if you have to stay fixed at psi equal to 0, you have to move with the interface. That is that quantity, that is the velocity of the interface. Huh? And this is just the local curvature. If it curves more, divergence n will be a larger, the curvature, otherwise it will be less. In particular, for a flat interface, which we know to be an exact static solution, grad n will be identically 0, i.e. the flat interface will not move in the Allan-Kahn equation. Okay, so the first thing, as I said, is we do dimensional analysis, and I have seen that there is a length scale which characterizes the domains. I call that L. What is the dimension of velocity? Speak up.
Length by time.
L divided by time, right? So basically, it's just the rate change. I mean, the bubble is expanding. It's just a time scale of rate. I mean, how the bubble is expanding, right? So that's the left hand side. What is the curvature? What is the curvature of the interface? It's basically, well, actually let me tell you, it's 1 over L. I'll derive this for a droplet shortly. The curvature is 1 over L. The more curvy the interface, the higher is the curvature basically. The smaller droplets have more curvature. As the droplet becomes infinite sized, you have less curvature basically, right? That's like a locally flat interface. So if you just sort of integrate that up, you get your first non-trivial result that the growth law, as I promised you, is just t raised to power half, just from dimensional analysis. I'll do this in a little more precise manner, but first I wanted to get the dimensional analysis out of the way. Is that clear, or is there any doubt? It's a good time to stop me. Huh?
It looks like the dimensionally both sides of the equations are not equal. Like left hand side is velocity, right hand side is 1 by L.
Well, you have other factors in here. You should put some constant in there. Let's say A I've already used. Let's say you put some constant alpha in there. Actually, that's just proportional to the surface tension. The surface tension is going to come into that.
How do we measure this L? Like what is the reference from which is point
Okay.
from which I
So that's a good point. You have these patterns, and it's clear by eyeballing it that there's a typical length scale of the pattern basically, right? How experimentalists measure it is they shine a beam of their favorite probe on it, and of course that beam depends on what the length scale of your phase separation is, of your phase dynamics is. Okay, so people shine light, people shine neutrons, people shine X-rays depending on what they're looking at. Okay, and the structure factor basically peaks at the inverse of the characteristic length scale. That's how it's experimentally measured. If you look at the correlation function, it's the rate of scale of the decay of the correlation function. I will talk about this later, but I just wanted to, I didn't want to introduce these concepts. But for the moment, let it suffice to say that if you just eyeball it, there's clearly a length scale. If you put down some horizontal line and you look at the zero crossings of the order parameter, that will give you a typical distribution of sizes. And that distribution will peak at some length scale. And that length scale grows with time because the pattern morphology grows with time. Okay, so typically it's this length scale, L, which grows as a function of time.
The structure factor has a clear ordering vector. Like it has a sharp peak.
Yes, yes, it has a sharp peak. Yeah, I mean,
Like in solids.
well, yeah, it's not that sharply peaked as in a solid because there is obviously all droplets are not exactly the same size. There's some there's some distribution, but it's reasonably sharp peak, and there's a clear maximum, and that's the reciprocal of the characteristic length scale, basically. Huh?
What is that term minus Ka? Like at the last, in the last equation?
Minus?
Yeah. Equal to like
Divergence of an
divergence of n equal to minus.
Minus divergence dot n hat.
Yeah, after that you wrote.
That's a curvature. That's the local curvature of the interface. That's just the definition of the curvature. Divergence n is the curvature. If the interface doesn't undulate at all, then there's no divergence, so the curvature is 0, basically. Okay, the other thing I want to point out is, but you should convince yourself of this, interfaces which bump outwards move inside. If you do the correct signs of the local curvature, they move inside. On the other hand, interfaces which bump inwards will move out. Okay? So, if you actually put the velocity down, this will go in that direction and this will go in that direction, and that is simply because you expect a locally undulating interface to become flat with time. Okay? Because locally that is your best bet. Globally, if you can get rid of the kink, you are even better off, but if you can't get rid of the kink, you should have a flat kink. That is your best solution. Okay? Okay, let us do a little more analysis of this Allen-Kahn equation. There is sort of interesting physics in here. When I have 15 minutes left in this lecture, I will just go back to the slides and sort of point out what all we have calculated in those slides. Yeah. But for the moment, let us do the following thought experiment. Examine the growth of a droplet of downspins of -1 in a background of upspins or +1. Okay? Because I know my coarsening process is consisting of disappearing of droplets and so on and so forth. So, I am looking at a droplet. Let us do it in 3 dimensions for specificity. So, let us do it in 3 dimensions. It has some radius r, which obviously depends on time, and this is a droplet of -1 in a background of +1. Help me out here, guys. Let us explicitly calculate all the things in the Kahn-Allen equation and figure out what is going on. How do you get divergence n? What is the curvature of a droplet? First, write down the n hat. What is the n hat on the surface of the droplet? Basic undergraduate algebra. Write down n hat in terms of x, y, z. नहीं लिखोगे? हाँ?
X cap plus y cap plus z cap divided by.
That's all it is basically. Yeah, it's just x over r, where r is the radius of the droplet, I hat, plus y divided by r, j hat, and because I am doing it in 3 dimensions, z by r, k hat. Right? That is the local normal vector. That is why I have taken a droplet. It is easier for me to take a droplet. What is the divergence of L? Help me out with this at least. Huh? Let us take the derivative one by one. So, this is 1 over r minus x squared over r cubed. Is that okay? That is the derivative of this guy with respect to x. R is x squared plus y squared plus z squared under the root, right? So, that is that, and similarly the other terms will give me 1 over r minus y squared over r cubed plus 1 over r minus z squared over r cubed. Yeah. So, basically you get the following term. If you combine this, this and this, that gives you minus r squared over r cubed, that is 1 over r. So, that is going to cancel with one of these factors. So, let us cancel off this guy with these guys. So, the curvature of your droplet when you have a perfect droplet is just 2 by r, and in arbitrary dimensions it is d minus 1 over r. Okay. Let's plug this into my equation, into my Allen-Kahn equation. What is the left hand side? The velocity. It's a perfect droplet, so the velocity is simply dr by dt. So my equation in this context is dr by dt is equal to 2r. Okay. Dimensionally, it's just what I got out there, right? Huh? But now I've actually calculated for a perfect droplet. Huh? So how to integrate this up? Help me here, guys. What is the solution? First, tell me, will the droplet grow or shrink? Let's check your intuition. Huh? Shrink. Why?
Minus 2 by.
We need the negative sign.
It's going to shrink, right?
Minus 2 by.
Minus.
Or did I miss the minus side? I'm sorry. Yeah.
Minus 10.
Yeah. Okay. So will it grow or shrink? It's going to shrink, and you can see that because at any value of r, this guy is negative, so the speed is going to come down. Okay. Very straightforward to integrate.
Physically, if you have to see it, like then you have to compare the surface, the energies there. Like why it should.
Because I told you the Allen-Kahn equation is saying that if I bump outwards, I move in. If I bump inwards, I move out, basically. So here I am bumping outwards. Locally, it will try to come flat. Because it's a perfect sphere, it will shrink similarly in all directions, and ultimately it will shrink to 0. Okay. So actually, if you integrate this up, you find that the solution is r0 squared minus rt squared is equal to 4 times. Okay. So if you start off with a droplet of size r0, it will vanish on the time scale. It will vanish on the time scale when this becomes equal to this. Basically, it's going to vanish at r0 squared time, okay, which is another way of saying that the growth law is t raised to power half. Okay. And in arbitrary dimensions, this is just, well, sort of obvious in arbitrary d. So, this is for d equal to 3. For arbitrary dimensions, this is just dr by dt equals minus d minus 1 over r, and you can just write the appropriate integral of that basically. Okay. So, if you start off with a droplet of minus 1 in a background of plus 1, it is going to shrink slowly and finally disappear, and the time scale of disappearance is proportional to the square of the initial size of the droplet. Okay. Which is another way of saying, so if you waited till time t, all the droplets of size t squared will have disappeared basically. Okay. No, sorry, if you waited till time t, all droplets of size square root t will have disappeared. Okay. And the only remaining structures will be larger than square root t, i.e. the characteristic time scale of domain growth is square root t. So, there is many ways of arriving at the same result, but maybe we can take a minute or two to answer any questions about this Allen-Kahn equation before I turn to another subject. Okay.
Sir, where we have incorporated the background this in this calculation, you said ki we have minus 1 this and plus 1 background.
See, these are the only two phases possible, minus 1 and plus 1. Okay. So, it does not matter whether it is a plus 1 in minus 1 or other way around. Both cases the droplet is going to shrink. Okay. And that solution is factored in the assumption that locally you have a kink interface. Okay. So, I am assuming that if I go with the normal coordinate, at the core of the this will be my one arm of the kink, and at the extreme distance it will be the other arm of the kink. Okay. Obviously, as the droplet shrinks smaller and smaller, that is a worse and worse approximation, right. That is only true for large droplets, but that's the usual approximation. Yeah.
You generate surface tension to be constant. 2 root 2 by 2.
Yeah. For in this dimensionless language, you'll have to reinstate the dimensions if you want the dimensional quantity. Okay, in this dimensionless language with the time dependent Ginzburg-Landau equation, I've got rid of all the parameters. But surface tension of course has energy, right? It's an energy, huh?
So during the evolution, this interface will change in their shape. It goes on time dependent changes.
Yeah.
So during that changes, it will always keep this surface tension constant.
Yeah, the surface tension is okay. Again, it's the same point in a different way. See, basically, I'm assuming that I have a flat kink, and then I'm getting the surface tension. So as long as the interface is in local equilibrium, that's the surface tension that applies. Okay. What I'm doing is even for the curvilinear interfaces, I'm making the approximation that locally a tangent profile applies, and in that case that's the correct surface tension. Yeah, if you have too much curvature, then it doesn't apply anymore locally. Okay, but I'm assuming, I mean people have assumed that the curvature is sufficiently small that you could have a local kink formation. Basically, it's like you're in a kink, huh? Strictly speaking, if you have any curvature, the kink solution is no longer an exact solution of the TDGL equation. That was a point, one of the points we had discussed earlier. Okay.
Radial droplet, we have lot of curvature.
Well, lot of is a sort of, I mean, let's be more quantitative. The curvature is 2 over r. That's the curvature. So for an infinite size droplet, you have 0 curvature. And for a, well, as the droplet gets smaller and smaller, this is a worse and worse approximation.
Shrink to 0 or some.
It will shrink to 0 finally.
So there will be only one phase remaining.
Because yeah, ultimately, that's the whole point. Ultimately, the system wants to get rid of all the interfaces in this non-conserved problem. It wants to get rid of all the defects which are raising my energy. And though I am using a word interface, but the same paradigm applies to vortex defects. Ultimately, if you have a superconductor, I'll show you a picture at the end of this lecture. As the coarsening takes place, the droplets sort of get systematically, the vortices annihilate with anti-vortices. They get annihilated, they become larger and larger, and finally you are left with no vortices at 0 temperature. At non-zero temperature, you will always have some finite density of defects in the final state. Okay, but at 0 temperature, you will have a perfectly aligned state. Okay.
So Sanjay, like it's just that I'm trying to make sure that I understood. So this shrinkage of this droplet, right? So this is how I would reconcile with your first couple of slides that you had with different phases. And if I wait long enough time, so then one phase emerges, right? Basically, completely sweeps the
Yeah.
So this is how I would understand that.
Exactly. Exactly. At the end of the day, I would have just either one would win out, but of course it's a, I mean it's a 50-50 thing which one wins out. At the lower temperature, the system is equally happy being up or down. All it cares is that it be magnetized. That's why I have turned off the magnetic field. As soon as I turn on the magnetic field, then one of the phases becomes preferred, and then this competing domains business goes away. In that case, you just have an invasion of the preferred domain, of the non-preferred domain. If you have a magnetic field, you have a preferred domain. The free energy becomes asymmetric, right? Huh? So if that's your free energy at h equal to 0, well, it should be symmetric. As you turn on the magnetic field, it becomes like that, right? So this is a preferred domain. So this guy just gets invaded by this guy at a constant velocity. That's another problem of pattern formation, but not as interesting perhaps as this one. But people have also looked at these invasion problems, and there are issues connected with the sort of speed of the front and things like that. It's been a rich subject, yeah, basically. But yeah, so that's how the without the magnetic field, though you have coexisting domains, you finally eliminate one by chance, basically. Okay. Any other questions? Yeah.
psi order parameter at the inside of the droplet, that will be proportional to T, like the minus T, like will decrease with respect to temperature, time, with at constant rate.
No, the order parameter will be in the bulk of the droplet will be -1 always. It's not going to change with time. In the bulk here, it's +1 always, doesn't change with time. It changes at the interface. Okay. And of course, at some point, the droplet will become small enough that that kink won't be allowed to properly saturate in the bulk of the droplet. Right?
For different structures, let's say for this spherical shape, it is always like we can. Will that be
Can you speak up a little bit?
Will that be similar for another structures, another?
Yeah. So, if you have random interfaces, the general I wish I had that picture with me, but I'll pull it up shortly. In the general picture, if you have random interfaces, you will locally become flat. Okay. And if you can get rid of that one flat interface, that's a fairly metastable state. But if you can get rid of that flat interface, also you will get rid of that also, and finally go to just one phase completely. Of course, how pure that phase is depends on how low you are below the critical temperature. At 0 temperature, you will have a perfectly pure all up state or all down state. But if you have some slight temperature, the up state will have impurities of down spins and the down state will have impurities of up spins. As you know, the magnetization goes to 0 at the critical point. So, that will still apply. Okay. Any more?
But as this droplet keeps shrinking, this assumption continues to hold all the way down.
Well, I mean, obviously at some point it's not good, but yeah. See, because it relies on the fact that the interface is a sharp interface. Okay. If it were very gradual, this would not be a good approximation. But the interface is sharp, and as a matter of fact, in these studies, it's usually approximated as a step function, which is something I'll come to next. Okay.
Also, in a usual bed, you will not scare the droplets, right? So you will get more random.
Bicontinuous structures, basically, yeah. But it's a nice sort of thought experiment whereby you can get the T raised to power half growth law in a very sort of controlled manner, and at the same time get to actually explicitly calculate the curvature, because I find students are somewhat fuzzy with the concept of curvature. So it's nice to actually calculate it explicitly. Okay. Any other question? Let me then move on to my next subject, which I'll maybe do out here. Okay, so now you have this pattern. You figured out the length scale as a function of time. And as I promised, I have used the kinks as a sort of instrument to capture the length scale. Okay. The next thing I want to do is sort of make a statement about the morphology. So you have this network of plus, minus, plus, minus, and so on and so forth. Yeah, and you have a morphology of some kind, and the next thing you want to do is capture the morphology. For this, people use what's called the correlation function, and the correlation function, which is something that I'm sure you've all encountered. If you take a point R1, let me use my language notes, yeah. If you take a point R capital R and a point capital R plus small r, the correlation between those points is a measure of how the system is interacting with itself. And near the critical point, that correlation becomes larger and larger. Okay. So, the quantity we always measure in both equilibrium and non-equilibrium stat mech is the correlation function, which is simply the order parameter at one point times the order parameter at another point time t, averaged over some non-equilibrium ensemble. Is that a quantity everybody's seen before? No, this is over the entire system, including self and outside also. Yeah. Has everybody seen this quantity before? Huh? Okay. You usually capture so you look at either two space points or you look at 2 time points. Yeah. At the same, then you look at things like aging and things like that, basically. Okay. So you measure either this is called the real space correlation function, and the other one is called the autocorrelation function. And I guess in the slow dynamics community, people look much more at the autocorrelation function.
The most general one is you have both R
Both
and
space
T,
and
then
time.
if you integrate over R, you have left with
That's right. Yeah. But normally, numerical guys and experimentalists look at this quantity basically. Okay. And this is, if you want to sort of define it a little more carefully, you should actually subtract off the average. So I've assumed here that the system is translationally invariant. So that doesn't depend on the starting point and the end point. Usually the system is also isotropic, the domains don't have a preferred direction. So you're looking at C RT, now it's only the magnitude, which is equal to 1 over V, an integral over the starting point dr psi r plus psi r t psi r plus small r t. That's that. And then if you want to subtract off the average, which people usually do, you also subtract off psi r t average and psi r plus small r t average. Okay. That's the full-fledged definition of the structure of the correlation function. And as the distance becomes further and further apart, you expect this variable to care less about this variable. So basically this expectation value is the product of the two expectation values. Subtract this off, and so you expect the correlation function to go to 0 at large distances basically. And you've all seen that it can go to 0 either exponentially or it can go as a power law. And so generically in StatMech we assume that it's some combination of power law and exponential basically, right? Is that something everybody is comfortable with? Okay. In this non-equilibrium context which I am talking about, you make the further statement. See, the claim is that the pattern is statistically self-similar in time. I'll show you the patterns in a few minutes if you've forgotten what I'd shown yesterday. But the patterns are statistically self-similar in time. That means basically the domain scale is increasing, but statistically the pattern is the same. Okay. It's, so one makes a statement of dynamical scaling, which is simply that in general you have a correlation function that depends on both space and time. That space time dependence is collapsed into the scaling variable, and this is known as dynamical scaling. For those of you who are familiar with dynamic critical phenomena, this is where this concept of dynamical scaling comes from. But I don't want to sort of go into the derivation. I just want to make the intuitive statement that the pattern at a later time is the same statistically as a pattern at a earlier time. It's just like magnifying it up basically, and therefore the length scale of the pattern becomes a scale factor for the spatial variable. Okay, that's the statement. Okay, so numerical and theoretical guys usually look at this correlation function. Experimentalists usually look at the structure factor, which is the Fourier transform of the correlation function, which means dr e raised to power I k dot r c r t. Okay. So, if you know one, you know the other obviously, but experimentally, as I just said earlier, if you do some kind of scattering experiment, typically the scattering cross section is proportional to S of kT. Okay. And because it's a non-equilibrium system, it depends independently on K and T, supposedly. Okay. But the fact that you have dynamical scaling actually gives you a collapsed dependence. Let me write down the collapsed dependent. What is the dynamical scaling form in this language? It's just L raised to power dimensionality, some scaling function f of k times L. Do you want me to derive that? Huh? It's very straightforward, but let's derive it. There's no harm, I think. Yeah, I shouldn't leave all the derivations to you. So let's get rid of this. So, how you derive it is basically you go to the definition. So, SKT, just plug the scaling form of the correlation form into the definition. That is equal to dr e raised to power I k dot r, and then I am going to plug in g r over L for the correlation function. Okay. Now, just introduce the scaled variable r by L is equal to x vector. Okay. And that sort of gives you the result basically. This will give you factors of L raised to power d. This will be dx. The limits will remain unchanged because they are from minus infinity to plus infinity. This will give you e raised to power I k L dotted with x, okay? And this will give you g of x, right. So, if you plug that in, you realize this is just some universal function of this variable. So, it is L d as I promised you f of k L. So, again theorists usually look at this, experimentalists usually look at this, they are equivalent descriptions, and if you know one, you know the other, and as a theorist we obviously want to find out a correlation function. Okay. Let me tell you a feature of the correlation function which has become very important in this literature and which you would encounter in any sort of, well, not any, but many statistical physics problems. Okay. So, this is the concept of what is called Porod's law. Porod's law is a statement, it is a physical statement about scattering from sharp interfaces. Okay. So, you have these Korsnig domains, there are interfaces, boundaries between the sort of various +1 and -1 regions. What does the scattering from these sharp interfaces give? So, I am going to actually explicitly calculate that. First, I am going to consider the one dimensional case, the result will just generalize easily to the case of arbitrary dimensions. It means that if you scatter a beam of light or something and you have sharp interfaces in the system, what will they give rise to in terms of the properties of the structure factor? Will they give rise to anything interesting? Okay. And Porod was not looking at phase ordering problems, He was actually looking at amorphous media, porous rocks, porous media. I guess this is very interesting to the oil community, right? They have to extract oil from porous media. So, in porous media you have empty spaces and you have rock. So, he found I think experimentally that the scattering has a very characteristic signature, which is now called Porod's law, and this applies to a whole host of systems with sharp interfaces in them. So, we expect it also to apply in the current context. Okay. And by the way, there are several generalizations of this Porod's law, which I will also refer to, but that will come later. Okay. So, the calculation in the 1D case is done as follows. You assume you have a kink like that, going from of dimension. So, that's along the sort of x direction, say, and that's psi of the kink, x or z if you prefer, it does not matter. It goes from, it is a size L. So, it goes from minus L by 2 to plus L by 2 basically, and the interface is located at 0, and the thickness of the interface xi is much less than the domain scale. Okay. So, I am going to operate on scales, that is how the derivation works. The scales are such that x is much less than the domain scale and much larger than the microscopic scale. Okay. And obviously, this is just to some approximation, this is taken to be psi x is taken to be a sine function as a function of x. So, wherever x is negative, it is plus 1, wherever x is positive, it is, I have done it here, yeah, okay, it is okay, minus 1 and plus 1, I should have drawn it the other way. Anyway, it does not matter, okay. Let us just take sine x, and I am going to actually explicitly calculate this quantity for a sine profile, and it is going to give you something interesting basically, okay. So, the correlation function C x is equal to, let us write this down in the definition, 1 over L minus L by 2 to L by 2 d x prime, let us say, an integral from, well, I can just call it x actually, I do not need an x prime. At one location the value of the order parameter is sin x, and at the other location is sin x plus, sorry, I didn't need I need an x bar here. So, it is sin x bar and sin x bar plus x there. That is the definition of the correlation function. Is that clear what I have written down? Huh? You guys are smart, you should have no problem following. I am just calculating this quantity for this specific case of a kink solution, and I have approximated the kink as a sine, I have taken it to be a sharp interface. Actually, it has some width, which is a microscopic width, but because you are working on length scales much larger than the microscopic width, it is effectively a step function basically, right? Huh? So, let us calculate this, guys. Kaise kare? This is 1 over L. So, basically, sorry? The mean is actually 0 in this case of the sine function, yeah. So I did not write that down explicitly, okay. So, this is 1 over L. Let me take the starting, so let me break up this integral. This is 0 to L by 2, and the starting, so I first take the starting point as lying within 0 to L by 2, and then I have here the quantity, let us write this down carefully, let me do this a little carefully, okay. so I don't get it wrong. So it's basically like this. X bar is a point sitting somewhere in here, and there are two possibilities for x bar plus x. Either it can sit on the same side of the kink or on the opposite, on the other side of the kink. So if it's on the same side of the kink, that's the 2 points right there. With distance, how much have I taken? X between them. And alternatively, it's on the and then you get +1 into +1. Alternatively, if it's on opposite sides of the kink, you get -1 into +1 basically. That's the contribution. So it's like laying a ruler down and asking whether what is the probability that the ruler will end up on the same side of the kink or across the kink basically. And obviously that depends on the length of the ruler. So now having sort of spelled that out in words, I can just tell you the answer is 0 to L by 2 dx bar sine x bar minus x plus, I have done some little shifting of limits and so on and so forth. You can just sort of do the 2 lines of algebra that goes with that. So it just I break up the intervals and sort of that's the calculation I do, and that gives me the following result: 1 minus 2 mod x over L. That's the correlation function. Okay, it's as simple as that. And this correlation function, as you can see, if the distance between the 2 points is 0, then it's just 1, because then obviously you have, I mean, you just, it's the same point you're multiplying the order parameter at, huh? But as the distance grows, you have some probability of hitting, of your ruler sort of sitting like that basically and hitting both sides of the kink. And this is what's called Porod's law. Why is it interesting? It's interesting because it actually has a singular behavior at x equal to 0. If you actually plot the Porod's law, see x versus x, it's 1 at x equal to 0 and then sort of comes down like that, right? It's a linear this thing like that. And if x is negative, again it's got exactly the same form like that because of mod x. So it's sort of singular at x equal to 0. The consequence of that singularity, I'm just going to sort of write down the answer because it would sort of not serve any purpose to calculate it. The consequence of that singularity is the following, that the structure factor has a what's called a Porod tail, and in arbitrary dimensions the structure factor is L raised to power d a d, so which is some amplitude factor, and the important quantity is this power law behavior in K. Usually in a scattering experiment, sorry, I am not making this sound very exciting at all, let me say it a little more carefully. In a scattering experiment, you expect a Gaussian tail, but because of the sharp interfaces, you have a power law tail, okay. And generally as physicists, we always, whenever we encounter power laws, we wonder what sort of gives rise to them. And in this case, and it's become really sort of popular in the community, you get a power law tail in the structure factor or a singular behavior as distance x goes to 0. Okay. That's the Porod's law, and if you have sharp interfaces, you get a Porod law in the scattering function, which is what I actually want to show you next, which is why yeah, I need 10 minutes here. Are there any broad doubts about it? It's worked out very well in that chapter I am going to send you, by the way, but are there any doubts about the calculation? Yeah.
Correlation, second line, you did the integration over R, but you kept the angular brackets.
CRT equal to 1 over V.
So I integrate over the starting point, but I keep the rod length fixed. Okay. So I average over R, The starting point is capital R and the end point is R plus R, and then I integrate all R.
So no, there is angular bracket now. Inside angular bracket
So
we
we are
have
asking
sine.
why the brackets are there.
Why the brackets are left? Because you still do it's a non-equilibrium ensemble you have to average over, na?
There you have not taken that side.
Yeah, here there is no ensemble. Here I'm just considering one solution, one cake, basically. But here I'm actually doing an experiment in this non-equilibrium ensemble where I'll have to do multiple evolutions of the same system and multiple noise realizations, etc. if I'm doing a Monte Carlo simulation. Okay, but this is just a sort of toy calculation for a single cake. Okay. Any other questions?
In these scattering experiments, can they also get like the frequency information?
They can actually, yeah. And
The full dynamical structure pattern.
I mean, somehow, ideally they should be looking, I mean, they could be looking at SK omega, but somehow the way these experiments have been done by, mostly by material scientists and metallurgists, they end up looking at this quantity, and the theorists end up looking at this quantity. Okay?
For this particular cake solution,
Yeah.
what is SK?
SK has some form, the tail of which is that. K raised to power minus dimensionality plus 1. Huh?
Is 1, 2.
D in this case is 1, but for arbitrary dimensions is D plus 1. I just,
So here it is L square.
yeah, for 1D it's L square. Well, L is not the important factor, the important factor is a K. Yeah, because normally you would expect a structure factor to have a Gaussian behavior at large K. That's a sort of normal expectation. But here you have a power law which is a consequence of this singularity and a consequence of scattering of sharp interfaces. Okay. Of course, we don't really have sharp interfaces, and maybe I'll remark on that if a little later. Any other questions? Okay, so can I get the slides back? Yeah. So this is sort of a colloquium I use to lecture on this material, pattern formation in the kinetics of phase transitions, and I just want to use some pictures. So far I have discussed, well, I told you what the problem is, I told you about the dynamics of ordering of a magnet and the dynamics of phase separation, and let's look at some results for the dynamics of ordering. So now you know the basic problem, you have an equilibrium phase diagram and you sort of quench from one region to another region and ask how the system evolves to its preferred new phase. It's a very universal problem in physics, especially in the context of phase transitions which occur in all kinds of systems. Okay. So the first paradigm problem was the dynamics of ordering of a ferromagnet. That's a phase diagram of the ferromagnet, temperature, magnetic field, and there's a critical temperature out there, critical point, and the experiment is you rapidly cool from here to here at late times. This is what we've primarily been discussing so far, and now these pictures hopefully are sort of make sense to you, but I'm going to make these sort of bulleted statements which I have not made so far. The first statement is of course that the patterns evolve in time. I start off at time t equal to 0 with a random mix of black and white, that's like an infinite density of defects. Then I develop domains in up spins which are black, domains in down spins which are white. There is a domain growth process. I have already told you that in the bulk of these domains not much is happening, but at the interfaces that's where all the non-equilibrium action is, and that actually obeys this Alan-Kahn equation, and then the domains grow and grow symmetrically until in a finite system you finally end up in all black or all white. Okay. In an infinite system the pattern will continue to grow forever and the process will be self-scaling. Okay. The system wants to get rid of these domain boundaries or defects, that is why the system sort of evolves, it phase orders. The velocity at an interfacial point is proportional to the curvature. I derived this Allen-Kahn equation, and you can think of if you just do dimensional analysis, sigma is just a surface tension which I put in because that drives phase separation. Then you find that the length scale grows in time as the square root of time. Okay. And a way of understanding that is that you can think of this interface performing random walks, this interface performing random walks. At sometimes the random walks meet, the domains coalesce, and then you have larger domains, and that is the process. Okay. The last thing I mentioned was that the system shows dynamical scaling. Now you can sort of see it reasonably clearly that the correlation function, which in general depends upon space and time because it is a non-equilibrium process, in this case depends on space scaled by the length scale, and that is the, so there is a scaling variable, and the scaling variable is R over L. Okay. Sorry?
Stem size or, I mean,
no, L is the characteristic domain size. Yeah. No, this is for an infinite system. Okay. The system size is not in here. So, L is the characteristic domain size, and the time dependence comes upon L's dependence on time. There is no independent dependence on time. That's the key point of having a scaling variable. Okay. And then finally, the last observation I made was that we've been able to use the motion of these defects to actually solve for the, approximately solve for the pattern, and this calculation was done rather well known paper in this field of Ota, Jaslau and Kawasaki, and basically they found the scaling function. They actually found explicitly the form of the scaling function. The most remarkable thing about the scaling function is that it has a Porod tail, which means the structure factor, which is what the experimentalists measure, at large k goes as k raised to power minus dimensionality plus 1. Okay. So, that is the ordering of the ferromagnet, and I have used, I can't solve this problem exactly, but I have used the sort of picture of these interfaces doing random walks to capture the pattern formation, and this scaled form of the correlation function actually captures the morphology to the extent that one is interested in doing so. Okay. And looking at these patterns, it is not hard to convince yourself that this is basically a magnified version of that, only the length scale of the domains has changed with time. Okay. I briefly mentioned, but now I am going to say some more about vector order parameter problem. So, this is the scalar order parameter problem. Let me now talk about vector order parameter problem. So,
what's the small k behavior of this S of k?
I mean, nothing very remarkable, nothing very remarkable.
Usually the long wavelength is the small k part.
Yeah.
And then the structure factor shows usually something.
Yeah, this is, yeah, it shows the universality the other way around basically. Any scattering of interface defects gives k raised to power minus dimensionality plus 1. Okay. So, now I am briefly going to mention a vector problem also, a problem with a vector order parameter. So, let us again, to use a language, this is a superconductor. A superconductor has a complex wave function, and in the superconducting phase you have the same wave function everywhere in the system basically. That's what is so remarkable about the superconducting state. It is a phase transition in our language, and one wants to study the following dynamics. If you start off at T greater than Tc in a normal phase, rapidly cool the system down to T below Tc, how does the system evolve into its superstate? So, this can be superconductor, it can be a superfluid, and so on and so forth. Okay. Okay. So, here is a picture of that evolution, and I particularly wanted to show you this picture because this I have not explained so far very much. Okay. So, let us start with this first bulleted point. The superstate is described by a quantum mechanical wave function. As we know, that has an amplitude. The amplitude is not very important, and we have a phase angle e raised to power I theta. In the Ginzburg-Landau theory of superconductivity, in the normal phase theta is incoherent. you have different values of theta everywhere in the system. In the superconducting or superfluid phase, theta is coherent. It becomes the same everywhere, and as you correctly pointed out, it can have any value between 0 and 2 pi, unlike the previous case where it could have any value between up and down, but here you have a continuous spectrum of degenerate states. So, what I am showing you in this evolution picture is a simulation of this vector TDGL equation, and I start at the different colors refer to different phase values. In the range 0 to 2 pi, I have picked 3 different, so there is a phase everywhere basically. I have picked 3 different small windows of phase angle basically, okay, that is what I have done. So, at time t equal to 0, the phase is incoherent, the different phase values everywhere else. As time goes on, some structure seems to emerge. Let us sort of follow it, the structure seems to grow. I bring your attention to this point here where 3 colors meet, okay. Basically that is my depiction. So, the 3 colors refer to 3 different values of the phase angle window. So, if you go round that central point, you clockwise you pick up a phase angle of 2 pi, and then there are other points, if you go round them you pick up a phase angle of minus 2 pi. These are what are called vortex defects, which I sort of referred to verbally, but now you can see what they are. There are points where the phase goes round in a, so the vector rotates round, and the singularity is right at the sort of center of that, where the order parameter is 0 basically. Okay. So, this particular vector process is characterized by the annihilation, and earlier I had the annihilation and collision of domain boundaries. Now, I have the annihilation and collision and of vortices and anti-vortices, and as a matter of fact, if you look out here, you can see just the process of collision taking place. Okay. A vortex is colliding with an anti-vortex, and then you are going to have a larger vortex and so on and so forth. Okay. So, again the paradigm is the same, the system wants to get rid of defects, and finally at time t equal to infinity end up in a state where the angle is the same everywhere, except as I said it has a larger degeneracy, basically it can point on the face of a clock. Okay. So, the domain growth is driven by the annihilation of these defects, and this was a problem that I and Alan Bray had looked at a long time ago and actually solved it exactly. We found the following results, let me share with you. The growth law is generically t raised to power half, but there is a logarithmic correction in 2 dimensions. Okay. That has to do with some irrelevant operator in, not irrelevant, marginal operator in renormalization group. Okay. More important, just 1 minute, let me just complete my statement and then I will answer your questions. Okay. We found also the scaling function. Again, in general it is a non-equilibrium process, so the scaling function should depend on r and t, but here it depends on the collapsed scaling variable r over the length scale is that, and we actually were able to obtain this function. It is a hypergeometric function, but we were able to sort of solve for it. The very nice feature of this function when we analyzed it was we found that earlier you had a Poirot tail of k raised to power minus d plus 1. Now you have a Poirot tail of k raised to power minus d plus n, where n is the number of components of the order parameter. Okay. So, for n equal to 1 you get back the old Poirot result, but in this generalized Poirot law, if n is 2 for vortices, then you get k raised to power minus d plus 2, n is 3 for Heisenberg model, you get k raised to power minus d plus 3, and so on and so forth. Okay. So, that is basically the again it is a non-conserved problem. The vortices are doing random walks in space, colliding, annihilating, giving rise to pretty much a random walk kind of growth law t raised to power half, but the scaling function has this generalized Poirot tail, and we not only solved it for n equal to 2, which is a superconductor, we actually solved it for arbitrary n, the problem. Okay. So, Ota, Jastrow and Kawasaki had done it for n equal to 1. we were able to do it for arbitrary n, and then this actually became subject of some conversation in the literature. This was all theoretical, but it was then experimentally verified in ordering experiments on liquid crystals at Bell Labs. Okay, so that became the first sort of validation of now what is now called the generalized Poirot tail. So that's one statement. Again, just to sort of emphasize the universality of this, I am talking of superconductors here. It's also the ordering of liquid crystals. Does everybody know what a liquid crystal is? You use it every day, right? Huh? You guys should know what a liquid crystal is. Liquid crystal in its simplest form is a assembly of rod-shaped molecules. The rod-shaped molecules energetically like to align parallel. Entropically, they like to be randomly oriented. Okay. So, what a liquid crystal is, where on the average the rods are lying parallel, but their centers are sort of liquid like, the centers are not sitting on a lattice. Okay. And this liquid crystal phase is of course what you use every day in your mobile phones and in your televisions when you go home to watch the cricket matches and stuff like that, right? Huh? So you should know what a liquid crystal is. I always give this example of a box of chalks. If you have a box of chalks, it's like the nematic phase where all the chalks are aligned up, and then you throw it on the floor, all the chalks are random, so that's like a isotropic phase, and that switching from nematic to isotropic is of great interest in the functioning of our screens. So, this also describes the ordering of a liquid crystal. Okay. Basically, the system, I mean, you can think of these phase, instead of phase angles, you can think of these as actual angles the rods are making. Okay. And it's the alignment of those rods as a function of time. Ultimately, all the rods are aligned in the nematic phase, but you have a 2 pi degeneracy in terms of where the rods can point. Or you can think of it as an electroweak theory with the Higgs boson giving mass to its partner particles. It's exactly the same symmetry breaking process which defines the kinetics of that also. Okay, so that's what I wanted to say about non-conserved dynamics. Tomorrow I think we'll move on to one lecture of what we know about phase separation. Our situation with the ordering is very comfortable. We have a pretty good understanding using these approximate pictures of defects annihilating and so on and so forth. Situation is not so comfortable vis-a-vis the phase separation problem, which I had warned you is a much harder problem. Let me remind you, in this case you can't just have random walks at the interfaces. Whenever an interface wiggles, all other interfaces have to readjust. So, it is a globally sort of coupled problem, and if you try to write down an Alan-Kahn equation, it actually ends up being an integral equation, in that the velocity at any point on the interface is an integral over the curvatures everywhere in the system basically. So, it is a hell of a problem which has proven intractable so far, and yeah, new ideas are always welcome. Okay, but we will do that tomorrow. I think I will stop for now. Huh? Any questions, etc.
You get the length at t is equal to 2, it's like t by ln t. It's not like some kind of critical dimension you are getting.
That's exactly. I'm very glad you raised it, because that is actually a critical dimension. See, okay. The point about these topological defects is that you have n, which is the number of components of the order parameter, and you have d, the dimensionality. So, n equal to d is the critical case. This is n equal to d, because I am talking about superconductor with n equal to 2 and d is also equal to 2. For d equal to 1, actually you do not have defects in this case. You can just topologically deform the defects away basically. Okay. Whereas, of course, for n equal to 1, you had defects even in one dimension, you had these boundary walls. Similarly, if n is equal to 3, you have monopole defects, but these only arise for d equal to 3 and greater. You do not have monopole defects for 1d and 2d. You can topologically deform these, continuously deform them and get rid of them in the system basically. So, these n equal to d is a marginal case, And that's where the logarithmic corrections are coming from, basically. You're perfectly correct. Sorry?
This picture is for d equal to 2.
Because this is a superconductor ordering, the number of components n is equal to 2, and similarly, I'm showing you these pictures in 2 dimensions, so that's the law for n equal to d.
How the picture will look like at night time? There will be 3 steps of this 3 colors, or
No, sorry?
how the picture will look like at infinite time?
So he's asking what is the phase order.
No, I got that.
Final.
See, it will go to one value of the phase angle everywhere. Okay?
In terms of colors.
It was one color, one single color. I have just shown 3 small windows of the phase angle. So this is 2 pi by 3 to 2 pi by 3 plus epsilon may be black, and so on and so forth. So it will all become one phase somewhere. If I showed you all the little windows, then the whole region would be colored, right? Huh? But so as to highlight the vortices, maybe there are better ways of representing this, but to highlight the vortices, I have just shown you 3 small windows of the phase angle. So at t equal to infinity, you'll break symmetry and you'll pick out one phase with the same color everywhere. Okay? Yeah.
You said like when d is less than n, the defects would get annihilated by topological twisting or
By topological deformation, yeah.
topological
So
deformation.
you don't have topological defects for d less than n. For d less than n, that's right, yeah.
So like how does like I cannot visualize like how topologically deform means, like if I am considering one dimensional XY model.
Yeah.
So like what is the, or like so that means there are no grain
So
boundaries.
you think of what a one-dimensional XY, it's like a row of pendula, right? And you can sort of have the pendula at any angle between 0 and 2 pi.
There will be like no two phases, all the
Unless you fix the ends, you can just sort of rotate it and get rid of any structure which you might put in the middle. A vortex would be some point which you go around and you pick up some phase. That won't be possible, basically. So 1DXY model is not of much interest for that reason. Okay. Okay. Any other questions?
When we say just defects, and when we just say defects or topological defect, both are same, or
They're the same. Topological defects. I mean, there are books on this, as a matter of fact. There's this well-known book by Chaikin and Lubensky of solid-state condensed matter physics, I think. They have large discussion. Lubensky is one of the bosses on defects in liquid crystals. So they have a good discussion of topological defects. There are also some reviews of modern physics articles on topological defects, and defect is like a bad word, but it's very important in physics, right? Like singularities, the best thing about complex functions is their singularities, right? Analytic functions are very boring. So similarly, defects are the most important thing about our theories. Okay? Okay, any other questions? Good. Then we stop for today and we meet at 11:30 tomorrow.